In year one, we looked at binomial expansion when you have a positive whole number as the power. So 1 plus x to the power 5, for example, or 3 minus 2x to the power 7. Effectively, our binomial expansion formula was an efficient way to save time when we're multiplying out a bunch of brackets. So 1 plus x times 1 plus x times 1 plus x times 1 plus x times 1 plus x would take you quite a while to calculate, even if you found an efficient way to do it. But the binomial formula allows you to condense all of that into a relatively efficient process. What we're going to look at this year is a way of doing something which we previously probably had no idea how to do. Unlike with positive whole numbers, there's no easy way of thinking about what 3 plus x to the power negative 5 means. We can't expand out a bunch of brackets, we'd still be stuck with a fraction involved, or a power of 3/4. That's something which involves a fourth root. So when we've got roots and reciprocals involved, something fundamentally different has to happen. But it turns out it's linked very closely to the same process we used last year. We just need to be a little bit creative with how we redefine things. To begin with, see if you can remember how the standard year one process goes. See if you can reproduce this 1 plus x to the power 4 if you've forgotten the details, and then have a go at using that expansion to find this very similar expansion, 1 minus x to the power 4. Have a think, see if you can make use of the result above to calculate the expansion below. And when you've done that, unpause the video and we'll continue. Okay, we should have something like this. The clever thing about this is the identity above, because that's what it is, an identity, it's true for any input value, for any value of x. We could put in x equals 3, and on the left-hand side, it would evaluate for me 1 plus 3 to the power 4 and give me an answer, which is 256, I believe. But you could also put the same input onto the right-hand side. 1, add 4 3s, add 6 lots of 9, add 4 lots of 27, add 81, and it would give you the same answer. Now, what we're doing here is like that, but instead of putting a number in, we're putting negative x in. Everywhere you see x has been replaced with negative x. And some of the time that makes no difference, like when it's 6 lots of negative x squared. Well, when you square negative x, you get the same as if you square x. But other times it does make a difference. When we have 4 lots of negative x cubed, that's going to be different to just 4x cubed, because the negative is preserved by the odd power. So we should get something like this. The negatives appear in the minus 4x term and the minus 4x cubed term, but the other three terms are the same sign as they were before. But you'll probably agree that's a much quicker process than going through the binomial expansion formula all over again for a very similar question. You might want to have a practice of this for yourself. See what happens when you try to use the same identity but apply a substitution that gives you 1 plus 10x to the power 4. You get quite a nice pattern with this one. You might want to try it out for yourself and see what happens. Next, we're going to look in detail at the two formulae that are provided in the formula book. At the beginning of any binomial expansion question, the first thing you should do is turn to the appropriate page in the formula book so that you know you're applying the correct rule. In year one, we got this with this extra bit tacked on the end as well. In other words, we've been using the choose notation, NCR, or N above an R. It looks a bit like a vector here, but it's not representing a vector. It's another form of notation for NCR. We've taken this from binomial distribution in statistics, effectively, or maybe statistics took it from here. But when we say something like 5 choose 2, what we mean is how many ways are there to choose 2 items from a collection of 5. So if you get to pick 2 ice cream flavors to put in your double cone and there are 5 flavors on offer, well, it turns out there are 10 different ways you can do that. One way to work it out would be to say, well, you can pick any of the 5 flavors for your first flavor, and then there's 4 other flavors left that you can choose from. So you're not allowed a double chocolate, but you might be allowed a chocolate and a strawberry or a chocolate and a vanilla. And when you've done 5 times 4, that gives you 20 different combinations. Although it's not quite 20 different combinations, because if you got a chocolate and a vanilla, and your friend got a vanilla and then a chocolate, well, all you need to do is switch your ice cream cone around and you can see they're the same. So if we account for the duplication, we end up with exactly 10 ways to choose 2 things from 5. And if you try 5 choose 2 on the calculator, that's the answer it'll give you. Now, what's going on behind the scenes is this stuff over here with the factorials. We're doing 5 factorial over 2 factorial times 3 factorial. That's effectively the same as saying how many ways are there to arrange all 5 flavors. It turns out there's 120 different ways of arranging 5 things in different orders. Then we divide by the number of ways to arrange the 2 that we're choosing, and we divide by the number of ways to arrange the 3 that we're not choosing. And it turns out that works out just the same as how many ways are there to choose 2 things from 5, or r things from n. You can have a think about why this is related to the binomial expansion if you like, but for now we're going to assume that you covered that in year 12, and we'll move on to how we can adapt it for year 13. First though, let's see if we can apply this formula. 2 plus 3x to the power 5. Look carefully at the left-hand side of the formula and the left-hand side of our identity that we're going to create, and think about which term is what. Pause the video, have a go at doing this for yourselves, and then unpause, come back and see if our answers match. Okay, we should have a is 2, b is 3x, and n is 5. So in theory, all we have to do is substitute those things into the formula. Of course, the formula goes on a while. We've got a power of 5, which means there'll be 6 terms, everything from the 0th power of x to the 5th power of x. And it looks like a bit of a beast. There's the n choose something bit, there's the 2 to the power bit, and there's the 3x to the power something bit. And it looks pretty horrible, but if we color code it a bit, we can see more clearly where all the pieces come from, and it's not quite so daunting. Every single term will either be one of the binomial coefficient terms, they're in red, 5 choose 0, 5 choose 1, and so on. Those are actually, for this question, they're the same as you get in Pascal's triangle, 1, 5, 10, 10, 5, 1. The next bit is descending powers of one of our 2 nomials. Binomial means 2 numbers. So one of the 2 numbers that I added in the bracket is 2, and we have powers of 2 going down from 2 to the 5 all the way down to 2 to the 0 in blue. And then we have ascending powers of the second nomial, 3x. 3x to the 0 is the same as 1, and then 3x to the 1 is just 3x, and so on. The reason I've put that 3x in brackets is because it makes a big difference. 3x to the 1, sure, it's exactly the same thing as 3x. But 3x in a bracket squared is not the same as 3x squared. 3x in a bracket squared means 3x times 3x, which gives us 9x squared. If we do the same thing with the rest of the terms, we get something like this. And finally, we can simplify it all down and we get this. 32, 240x, 720x squared, 1080x cubed, 810x to the 4, and 243x to the 5. Bit of a mouthful, but that is the complete expansion for a standard positive integer power. Now, this is the year 2 formula. And at first glance, it looks very different. For a start, the left-hand side isn't quite the same. It's got 1 plus x inside the bracket instead of a plus b, so it seems to be more restrictive. In reality, the fact that that's x, as we've already seen with a minus x, doesn't matter too much to us. I'm happy to replace x with 10x or minus x or 2x or a half x or whatever else I need, as long as I replace every instance of x and I'm careful to square the entire thing if it's x squared and so on. But then the other bits, they look a bit strange as well. Instead of having n choose 1, we seem to have an n. And instead of having n choose 2, we've got an n times n minus 1 over 1 times 2. Now those terms should look a little familiar. They're kind of like the factorial terms, a number multiplied by the one below it, and then on the bottom 1 times 2, that's just 2 factorial. So there's something going on in here. There is a connection between these two, so let's investigate a little bit and see if we can tease out what it is. Let's start by looking at a straightforward example for the first one. We'll do 5 choose 3. How many ways are there to choose 3 things from 5? Now if we apply the formula given over here, we can see that we can pull this apart into factorials. Not only that, but once it's written as 5, 4, 3, 2, 1 over 3, 2, 1 times 2, 1, we can see that there's some stuff that can cancel out. Now you might have thought of cancelling out the 3 as well, but I'm going to leave it in for now because it'll be easier to see the more general pattern in a moment. The key idea here is that that second term on the denominator, the 2 times 1, definitely also appears in the term in the numerator, 5 times 4 times 3 times 2 times 1, which means that bit can cancel out, and we essentially end up doing 5 times 4 times 3 and then dividing by 3 times 2 times 1. And that gives us an answer of 10. There are 10 ways to choose 3 things. You might remember previously we said there are 10 ways to choose 2 things from 5. Well, the symmetry of the situation means if you're choosing 2 ice cream flavors from 5 options, then at the same time you're choosing 3 of them to not have. So if you choose chocolate and vanilla, then it's equivalent to not choosing strawberry, rum and raisin, and blueberry or whatever it might be. So when you choose 2 things, you are simultaneously not choosing the remaining 3 things. So choosing 3 or choosing 2 from 5 ends up being equivalent. That's why there's symmetry in Pascal's triangle and symmetry in the binomial coefficients. Now, that's all well and good for the year 1 version. And it's worth noticing at this point that when we cancel things down, n factorial stops being n times n minus 1 all the way down to 1 because we've lost a couple of the terms at the bottom. We've lost the 1 and the 2. Now, what happens when we try it for the year 2 version? Well, we can't do factorials. We can't define -7 factorial or 3/4 factorial. It doesn't really work if we're multiplying by each number one below that, one below that, all the way down until we get to 1. We have a problem if we never get to 1. If you start at -7 and you keep going down, you just go down further and further, -8, -9, -10, you're never going to reach 1. And similarly, if you start with a fraction, even if it's a positive fraction, like 1.5, if you keep going down in ones, you're going to get to a half, and then you're going to miss 0 out and go to -1/2, and then -1.5, and so on. So we never hit 0, and therefore we can't really do factorials with those weird numbers. But what if we write out what it would look like and not bother too much with the weird infinity nonsense going on? This is kind of what you might get if we tried something strange like -2 choose 3. Well, -2 factorial doesn't make much sense, but if we think about what it means in the same sense as 5 factorial, keep multiplying by numbers one lower than that, and so on until you get to 1. We never reach 1, so we keep going forever. And that same issue happens on the bottom. You've got to think carefully about this, but the bottom term there is n minus r factorial. So the bit in blue is -2 take away 3 factorial. And that still cancels in the same way that the previous example did. So compare it to the one above, there's no difference, apart from the fact that what's cancelling out now is that pesky infinite sequence of numbers that were being multiplied. That term effectively was infinity over infinity, or possibly minus infinity over minus infinity, depending on how many terms you've got. Of course, it's an infinite number of terms, so maybe it's both, and it's something weird. But if we cancel out everything from the -5 times -6 onwards, we're left with a sensible, finite value, -4. Somehow it works. Now, we have to be a bit cautious whenever we're playing with infinity, but luckily, cleverer mathematicians than you or I have worried about this in the past, and they've got some little clauses and small print that we'll look at in a moment that allows us to do this and get sensible answers that we can actually work with. First, let's see what happens when we try this with a fraction. Here's a half. If we try a half factorial and we use the same kind of logic, we'll get a half times -1/2 times -1.5 and so on forever. But then we also have a -2.5 on the bottom. So we try to make a factorial out of that and we get an infinite sequence of numbers multiplied again. However, we can still cancel. All of that pesky stuff in blue on the bottom cancels with an infinite chunk of whatever's on the top. And we're left with, again, a sensible looking answer. We get 1/16 for this one. And again, once more, we see a pattern. This is n times n minus 1 times n minus 2 over 3 factorial. It may not always be possible to write things like half choose 3. This doesn't really make sense. This is a slightly dodgy way of writing it. And we can't write a half factorial. It doesn't make sense. But if we relax our restrictions about that temporarily, we can see why maybe there's something behind the scenes that we can still pull out of the other end. Even though somewhere along the way things don't make sense, something at the other end does make sense. And that is where the second formula comes from. You can see the n times n minus 1 over 2 factorial right there. Well, this one is the next term. That's the one that goes in here, somewhere just after the x squared term. That's the coefficient of the x cubed term in the binomial expansion. And you can see the more general term, if you try replacing r in here with some other term like 4 or 5, you can get a sense that this pattern continues. The fifth term, or the fifth power of x rather, will have a coefficient that looks like n times n minus 2, or 1 times n minus 2 times n minus 3 times n minus 4, all over 5 factorial multiplied by x to the 5. You can just sub in values of r, and you'll see how far that numerator goes, and you'll see that the factorial term on the bottom corresponds to the power of x on the top. Now, one thing that we recognize as soon as we start calculating these expansions is that they never end. So if we were doing an ordinary binomial expansion with 1 plus x to the power 4, we never get any terms greater than x to the 4. We'll get a constant term, we'll get an x squared, an x cubed, an x to the 4. We won't get an x to the 5 term. And that's because eventually, if you keep going, you'll get to a point where you're multiplying by 0. And everything from that point on has 0 as a factor. There'll be 0 x to the 5s, 0 x to the 6s, and so on. However, if we have a negative or a fractional power, we get an infinite expansion. I'll show you with an example, and then you'll see how it works. That's why in the questions they'll say find the first 4 non-zero terms, or they might say find the binomial expansion of this up to and including the term in x squared, or something along those lines, something that tells you to stop after a certain point. Otherwise, you'd literally be there forever. Step 1 is to look at the formula. Go to the formula book, check it out, make sure you're applying it appropriately. The next thing to do, just like with any formula, is make sense of what the different pieces are in that formula. The formula has 1 plus x to the n. We have 1 plus 2x to the minus 3. Now the n is normally the simple one to spot, as long as you don't have to do anything fancy, like maybe this had been written for us as 1 over 1 plus 2x cubed, and we'd have to recognize that we can write it as a negative power and then apply binomial. But the other bit inside, the x, that's a bit harder, because it's x in the formula book, but it's 2x for us. So we've got to recognize that wherever we see x appear in the formula, we need to write it as 2x. And that means if it says x cubed, we're going to have 2x in a bracket cubed, which is the same as 8x cubed, not the same as 2x cubed. The next thing to do is just start calculating terms. We can look at the expansion above 1 plus nx plus and so on. And we keep going until we have a sufficient number of terms. We've been asked for 4 terms, so that's how many we'll do. The first term is nice and straightforward. It's a 1. And then we need n times x. Well, our n is negative 3, and our x is 2x. So that's our next term. Then as we move forwards, we can make use of what we've already got in a way. We've already got minus 3. The next term will have an n, but it will also have an n minus 1. So we'll have minus 3 times the next number down, which is minus 4. And the power of x will increase. In this case, it's a power of 2x. So we'll have 2x to the power of 2 instead of just 2x to the 1 like we had before. And we're also going to need to bring in this 2 factorial term. Now, sometimes people miss this out, the 2 factorial on the bottom. And especially when we get to the next term, they might forget the 3 factorial that belongs on the bottom. Because the next term we have minus 3 times the next one down minus 4 times the next one down minus 5 times a higher power of x, 2x cubed, but then divided by the factorial of the power of the x term. If you find yourself forgetting the factorial term, one thing you can do is deliberately write in the 1 factorial that's hiding in the first term that we don't really care about, or even the 0 factorial here, although that can be a bit more confusing because technically 0 factorial is 1, but the reasons for that are a little hard to make sense of. I definitely write 2 factorial instead of writing 2 because although they are the same thing, it reminds me that when I get to the next term, I need 3 factorial, not just 3, because it does make a difference there. Now I've already got 1, 2, 3, 4 terms, so I don't need any more. The question asked me for the first 4 non-zero terms, but I need to be a little careful with my notation because it would be wrong to say that 1 plus 2x to the minus 3 is exactly equal to what I've got written on the screen. So I normally put a plus ... at the end. Another option here is to use a roughly equals sign, that wiggly equals sign, instead of an exactly equals sign. And that shows that, at least for certain values of x, provided we satisfy the small print here, as we'll get to in a bit, that the terms you've written out are roughly equivalent to the thing you started with. We have to accept that what we're looking at here is a bit like approximating 1/7 as 0.143. It's about right, but it's not quite all of it. And no matter how far we go, we'll never be able to completely exactly represent it unless we find some clever way of describing the entire thing. So we stop after 4 terms and we put a ... and ellipses at the end to show that there are more terms, but I've just not written them down. Now the next thing to do is to simplify. So we go through and either with a calculator or carefully by hand. If you're doing it by hand, I would recommend you first look at the signs. So see how many negatives there are in the entire expression that you're trying to deal with. And then next you look at the number inside the bracket with the x, because if it's 2x in a bracket squared, that's going to give you a 4. If it's 2x in a bracket cubed, that'll produce an 8. And then you multiply all of the terms in the numerator, divide by whatever's in the denominator, so you can simplify it correctly. So this is our expansion. And technically, we're finished here for this particular question. However, if you can, particularly while you're learning this topic, it's a good idea to verify your answers. You can either do this, as you'll learn about in a bit when we start looking at approximations. You could do it by just substituting in a very small value of x. It's got to be a small value for reasons that will become clear in a moment. But you could try on a calculator putting in, say, 0.1 into the left-hand side and 0.1 into the right-hand side and see how closely they match. They won't be perfect, but if x is small enough, then they should be similar. The other thing you can do, which is very quick and simple, you just can't do it in the exam, while you're learning and while you just want to test that you've done things correctly, go to Wolfram Alpha. It's free online. You can type in 1 plus 2x to the power of -3, and if you scroll down a bit, after it shows you some graphs and things, it will show you what's called the series expansion at x equals 0. And it should show you the first few terms. If you need more terms, you can just click on a button that says more terms and it'll calculate a few more for you. So that's a nice quick way of verifying that what you've got matches what you should have. Now we come to this slightly thorny question. What's the good of an expansion that goes on forever? If we can never write it all down, what's the point? Surely it's just a longer, more complicated way of writing something that we've already written. And if we can't calculate with it, why bother? Well, that same argument could go for the expansion of a third. 0.333 may not be equal to a third. It isn't, it's a bit too small, but it's a pretty good approximation to a third. It's close enough for most practical purposes, and so it's a useful value to have. Not only that, but it's a lot easier to do calculations sometimes with an approximate value than it is to try to get an exact value. This, for instance, this is the reciprocal of the cube of something. It's 1 over something cubed, and that's not an easy thing to calculate directly. And if you are programming a computer or a calculator to do this kind of computation, you would need to explain to it how to do it by building up from the things it knows how to do, which is counting, adding, and then if you do lots of adding, you can get multiplying by whole numbers, and you gradually build up to things like powers, which is basically repeated multiplication, as long as the powers are positive whole numbers. But the process that a computer will need in order to find a reciprocal or a root or something like that, which is basically a power that isn't a positive whole number, is exactly this, a binomial expansion. And it will look at just the first few terms. It might look a few more terms than we've got here if it wants an answer that's going to be exact to, say, accurate to 10 decimal places to show on your calculator screen. But it's not going to do anything more sophisticated than exactly what we've got here. It's going to do 1, take away 6 lots of the input value plus 24 lots of the input value squared, take away 80 lots of the input value cubed. And as long as the input value is small enough, then this should come out as something pretty similar to 1 plus 2x to the -3. Let's do a quick comparison. I threw this into a spreadsheet so we can see what Excel calculates for an exact power of -3. And then we can see what the approximation gives us. And then I've got a percentage error there. You can see that they're exactly the same, provided x is equal to 0. And then when x is close-ish to 0, the numbers are coming out pretty good. So 0.75 instead of 0.7513. We're looking at x equals 0.05. and then 1.37-ish when x is minus 0.05, and so on. However, the approximations get pretty useless if you go too far. Minus 0.3 is nowhere near. We're 50% off. Basically, the approximation is massively underestimating. And by the time we get to positive 0.25, our approximation is actually giving us a negative number, whereas the exact value is 0.3-ish. We're getting minus 0.25, so we're out by huge amounts. However, within a fairly narrow range, we're getting reasonably decent approximations. It might be even clearer to see if we look at this on a graph. If we have y equals 1 plus 2x to the minus 3, alongside y equals our big messy cubic that we've created. The dotted line shows the cubic equation, y equals 1 minus 6x plus 24x squared minus 80x cubed. You can kind of see that it's a cubic. It goes up to the left, it goes down to the right. And then we've zoomed in a bit on the graph so you can see the bit where they're the most close to each other. And that seems to happen best when we're give or take 0.05, something like that. They're not far off when you get up to 0.1 or minus 0.1, but they start to drift somewhat alarmingly when we get closer to a quarter. This is where we come back to the small print. You might remember this type of expression when we looked at geometric series and a sum to infinity. That was when we were coming up with a way of measuring and calculating the total of a series of numbers that just went on forever, and yet somehow we could still find a meaningful value when we added them all up together. The only stipulation was we needed the common ratio to be smaller in size than 1. It could be positive or negative, but it wasn't allowed to be as big as 1 or as low as minus 1. It had to be somewhere within that range. Up to 0.9 something or down to minus 0.9 something was the most you could go. And if that happened, then increasing powers of r would just get smaller and smaller. And that's what happens here. We'll have x cubed, and then the terms that we've missed that go beyond what we've currently got will be an x to the 4 term, an x to the 5 term, x to the 6, and so on forever. But if x is really small, like 0.1, or even better, 0.01, then x to the 5 is going to be incredibly tiny and will have very little impact on the actual value that comes out the other end. Now, in our case, we have to be a little more cautious because we did 1 plus 2x to the power of minus 3. So the x that's referred to in the formula book in this limits of validity statement, that's what this is, it's telling you how far you can go and still have a valid expansion. Our value is not really x, it's 2x. We need to remember not just to sub in 2x into the standard formula when we do the expansion, but also to put it in when we look at the limits of validity, when we take a close look at this mod x is less than 1 statement. So instead of putting mod x is less than 1, we're going to need to put mod 2x is less than 1. And the modular signs here are basically saying the size of 2x is limited by 1, which means that 2x itself is allowed to be negative, perhaps, but it's not allowed to have a size greater than 1. So it's stuck between 1 and minus 1. And then all we need to do is divide all 3 sides of my inequality by 2. And we get x between minus a half and a half. Now, minus a half and a half seems like a fairly restrictive range, but even within that range, we find that our approximation doesn't do a particularly good job for many values of x. This animation is showing you what happens if you do your binomial expansion to initially just the highest power of x being x to the 0, so we get a constant, which only matches when x is 0. And then we try something linear, which would be like a binomial expansion up to and including the x term. And then we have the quadratic one, the cubic, quartic, quintic, sextic, etc., etc. And each of those is increasingly good at approximating our true function. And yet, because it's a polynomial, we can see the oscillation as it goes from even, odd power for the highest power. It's never going to be perfect. And yet you can see it matches pretty well for the negative numbers that it's showing. And it's matching increasingly well for the small positive numbers. The key thing here is that although the infinite expansion is definitely only valid between plus and minus a half, any finite expansion ideally wants a really small value of x to be good. So there are 2 aspects to this. One, the expansion is definitely not valid if x goes above a half in this case, or below minus a half. And 2, the expansion will give you a good approximation when x is small, and it will be an increasingly good approximation as x gets increasingly small. The closer you are to x equals 0, the better this approximation gets. Now we're going to have a quick comparison between the two formulae, just so we can look back, we see what we like about each one. For the year 12 formula, it is certainly simpler looking. There's less weird fractions involved because that's been delegated to the NCR term on the right, I suppose. And also, a big advantage is that it lets you work with any two terms. You just need to figure out what your A is and what your B is and put them straight in there. The massive downside is that it will only work with positive integers. So it's a handy one to have when you've got positive integers, but if you're stuck with negative integers or you're dealing with fractions of any sort, you're going to need to work with this second one. Now, it is more complicated looking. It's got fractions involved, and we've got to interpret the n-1 brackets on the top. Also, it requires special treatment if the first term is not 1. We have 1 plus x to the something. Now, we are going to cover how to deal with that, and it's not hugely complicated. It's one little step that has to happen at the beginning of the question to convert your question into one that matches this formula. But still, it's an extra thing you've got to do, which you wouldn't have had to do with year 12. But the one big plus about this is that it works for any power. You're going to have a more sophisticated formula in order to deal with powers that are not positive whole numbers, and that's exactly what this is. Now it's time to practice a few for yourself. And the first thing you'll probably notice here is that none of these look like binomials, and yet they are only one step away from being in the correct format to match the left-hand side of this equation. So, before you begin, interpret the roots or the reciprocals, write your expression as a binomial. Think of it as 1 plus x to the power of something. And then have a go at expanding using this formula. Pause the video, try these 3 questions, then come back when you're ready. Okay, the first thing we should be able to do is turn 1 over 1 plus x into a binomial term, 1 plus x to the minus 1. We can do the same with square roots. A square root is just a power of a half. And then an inverse square root, you might call this one. It's 1 over 1 plus x to the half, which means it's 1 plus x to the minus a half. Don't be tempted to just do 1 over the previous expansion, because what you'll end up with is not a polynomial. It'll be an infinite polynomial on the bottom of a fraction, and that's nothing like as helpful as having a polynomial. Now we're going to apply the formula. If you do it correctly, you'll find this first one comes out looking quite nice. These alternating terms for x. In fact, if you're curious, you can think of this expansion as a geometric series, an infinite geometric series. Think carefully about what your common ratio is, what your first term is, and maybe work out the sum to infinity and see what you notice. For the next one, we get something rather different. You might think there's a pattern going on, and then suddenly a 5 appears on the top, so you've got to watch carefully for all of the terms so you don't make any assumptions about where this is going. And the last one we should have 1 minus a half x plus 3/8 x squared minus 5/16 x cubed. Now you might want to think next about what you would do if you had 1 over root 1 plus 2x instead of just 1 over root 1 plus x. We've already got a formula for 1 over root 1 plus x, so could you, without doing too much extra work, generate an equivalent expansion for 1 over root 1 plus 2x? Think about the substitution you'd need to do. Now you can have a go at a couple of questions from the book. Exercise 4a, questions 2 and 3 will be good ones to start with. Once you've done those two, you can have a go at questions 4, 6 and 7. You skip out the other ones for now. We're going to work on approximations using binomial next time.